Hi, I'm Lisa.
Hi, and I'm Jeff, and we're with Uberflip. Uberflip is a marketing company that helps businesses create personalized content experiences at scale. The data science team is tasked with finding innovative ways to make personalization even easier, faster, and more scalable. One of the ways that we can do this is by using machine learning to identify groups or clusters of similar people. What we can do with this information is by understanding more what people are actually interested in reading. One of our biggest challenges that we're faced with is decoding what features that we want to use. Specifically, we have a lot of different data available to us. We have demographic, firmographic, we have text and image data, and we have behavioral data, what people are consuming. What we need to do is parse all this information and find out what is actually really important. The traditional way of doing this is with a lot of domain knowledge and feature engineering and dimension reduction, but we can now use deep learning as a way of pre-learning, having the model do the feature engineering for us. So the paper that we chose proposes a taxonomy and workflow by which deep learning researchers can build their models and explain their models. The proposed taxonomy and framework for building clustering models is as follows. Step 1, build the main architecture, then determine the number of layers, and then focus on the loss functions, specifically the non-clustering and then the clustering loss functions. And then we need to find a way to combine the loss functions. And as a final step, we update the cluster assignments. Now, Lisa will talk about what this means in more detail.
So as Jeff mentioned, we have maybe thousands of features, and we can include all of those as input to our neural network model. Upon training, it will simultaneously learn a clustering-friendly representation of those features and identify the clusters. The first decision we make is what the main neural network architecture will be, and this choice depends on the domain of the problem. If we're clustering images, a convolutional neural network would be a good choice. But if the goal is to find latent representations, a variational autoencoder is often used. Next, we have to decide which of the layers to use for clustering. For example, we might use the output layer, a middle layer, or multiple layers. Once we've chosen the model architecture, the next step is deciding on how to train it. Although our goal here is a non-clustering loss function is often used to force the model to learn a useful representation of the input. For example, we could train the model to perform a related supervised prediction task, and then use the standard mean squared error loss function. Or we could apply an autoencoder loss function, which will train the model to recreate its input from the latent features it creates. Another option is the self-augmentation loss function, which will train the model to create an output from the raw data that closely matches the output it creates from a transformation of that data. In addition to these non-clustering loss functions, a clustering loss function can also be used. This helps assure that the latent representation learned by the network will be clustering friendly. For example, we could use the k-means loss function, which will train the network to find a latent representation where the clustered data points are close to their centers. Similarly, we could use the locality preserving loss function. Both of these are hard clustering loss functions, meaning that each point is assigned to only one cluster. Another option is to use soft clustering, which means that the points are assigned to every cluster according to a probability. We can then use the clustering assignment hardening loss function, which will seek a representation where those probabilities are all near 0 or 1. The benefit of the soft clustering option is that the parameters for cluster assignment can be updated simultaneously with the model. If we use one of the hard clustering options, then we'll need an extra cluster assignment step. Now you have to decide on how to combine the loss functions. For example, you can pre-train your model on the non-clustering loss, and then fine-tune the model in a separate step by only considering the clustering loss. Or you may choose to joint train by choosing some other alpha, or you can vary alpha according to a schedule.
So the main takeaways of the papers are as follows. Basically, the authors say that taxonomy enables a more systematic and analytic approach to creating new methods. By decomposing existing methods according to the building blocks of the taxonomy, we can analyze commonalities among good methods and attribute limitations to specific building blocks. We're also able to identify higher-level model features and components that create generalized models. We can also use this taxonomy and framework to better explain our model so we can increase model reproducibility in our literature.